Let's now walk through an example where we are going to solve a system of first-order linear differential equations for the case where we have complex eigenvalues. We're going to be finding the general solution of the system of equations dx dt is equal to minus 3x minus 2y, and dy dt is equal to 5x minus y. The first thing that we're going to do is write the system in matrix form. I'm going to start by letting vector x be a vector with components x and y. This gives us the derivative with respect to time of our vector x that has components x, y. And this is going to be equal to minus 3, minus 2, 5, minus 1. That's our matrix made up of the coefficients, if we look back up here, from our system of equations. And then we multiply this by x, y. We can then write this as the derivative of vector x with respect to time is equal to a matrix A times x, where we're going to define matrix A to be minus 3, minus 2, 5, minus 1. In step 2, we are going to find the eigenvalues of our matrix A. There's our matrix A. There are two ways that we can do this. We can solve the determinant of A minus lambda I is equal to 0, or we can solve the equation lambda squared minus the trace of A times lambda plus the determinant of A is equal to 0. Let's solve the one on the left first. We have our determinant A minus lambda I. That just means that we're going to subtract lambda off the main diagonal elements. And we're going to set that equal to 0. This gives us minus 3 minus lambda times minus 1 minus lambda minus 2 times 5. That's just the main diagonal elements multiplied minus the off-diagonal elements. This gives us lambda squared plus lambda plus 3 lambda plus 3 plus 10 is equal to 0. So we have lambda squared plus 4 lambda plus 13 is equal to 0. Before we solve this, let's go over here on the right and look at finding our quadratic using this formula. We have lambda squared minus the trace of A. The trace of A is where you take the main diagonal elements and you add them. So this is minus 3 minus 1 times lambda. And then we have the determinant, which is the main diagonal entries multiplied. So that gives us a 3. And then we have a minus the off-diagonal entries multiplied, which is minus 10. So this gives us lambda squared plus 4 lambda plus 13 is equal to 0. Now let's go ahead and let's factor this. I'm going to go back over here to the left. Let's first look at the discriminant. Our discriminant here is b squared minus 4ac. And that's going to be 16 minus 4 times 13, which is 16 minus 52, which is minus 36. So this is negative, which means we're going to get complex roots. So we don't have to worry about factoring it. Let's just use the quadratic formula. Lambda is equal to negative b, so that's minus 4, plus or minus the square root b squared minus 4ac, but we already computed that, and that was minus 36. So we have a minus 36, and we divide this by 2 times a, which is just 1, so that's 2. This gives us minus 4 plus or minus 6i, all divided by 2, so we get that lambda is minus 2 plus or minus 3 times I. We'll highlight that because those are our eigenvalues. And let's just make a note that we have complex eigenvalues. That's going to tell us the form of our general solution. In step 3, we are going to find the eigenvector associated with our complex eigenvalues. The nice thing about having complex eigenvalues is we only have to find one eigenvector. We're going to find it by solving the system of equations A minus lambda I times vector V is equal to 0. Let's remind ourselves what matrix A is. It was the matrix minus 3 minus 2, 5 minus 1. And I'm just going to arbitrarily choose that vector V is equal to AB. Let's now go ahead and let's set this up. A minus lambda I is going to be minus 3 minus lambda minus 2, and then we have 5, and we have minus 1 minus lambda, and we're going to multiply this by A and B. That's N for vector V, and it's equal to 0, 0. In step 2, we found that our eigenvalue, at least one of them, was minus 2 plus 3i. I think it's just easier to work with the positive imaginary part. Let's now plug this in. We have minus 3 minus lambda, so this is minus 2 plus 3i. And then we have a minus 2, we have 5, and then minus 1 minus a minus 2 plus 3i. And this is going to multiply AB, and it's going to be equal to 0, 0. Let's go ahead and let's clean up our algebra. We have minus 3 plus 2, so that's minus 1 minus 3i, and then minus 2, and then we have a 5, and then we have minus 1 plus 2, so that's 1 minus 3i. And we multiply this by AB, and we get 0, 0. Now let's find our equations. If we multiply this out, we get minus 1 minus 3i times A minus 2 times B is equal to 0. And then we'll go ahead and do the next one, 5a plus 1 minus 3i times B is equal to 0. It doesn't really matter which one of these we choose to solve. They're actually equivalent, even though it's a little hard to tell that because of the complex numbers. I'm just going to choose to solve the first one, and I'm going to solve this for B. So we're going to write down that B is equal to minus 1 minus 3i times A all divided by 2. To avoid fractions, I'm going to choose to let A be equal to 2, and then we get that B is equal to minus 1 minus 3i. Now we can write down our eigenvector, vector V. Remember that was equal to AB, and this is equal to 2, and then minus 1 minus 3i. I'm going to highlight this because we're going to need that in just a minute. Now we're at our final step, and that is to write the general solution. Over here on the right, I've written down what the general solution looks like for when we have complex eigenvalues. In our solution, we found that lambda was equal to minus 2 plus or minus 3i. So that means that alpha is minus 2 and beta is equal to 3. Let's also go ahead and let's write down our vector V, even though it's right up there. This way we'll have it all together. We have 2 and then minus 1 minus 3i. Let's now look at our solution. Our alpha is up here in the exponent, and then our beta is right here in our trig functions. And then we have our vector V, which is our eigenvector. We have to split it into its real part and its imaginary part. Vector A is the real part, and vector A is right up here, And then vector b is the imaginary part, and that's right there. Notice too that we have a negative sign right there that we have to watch out for. Before we write down our solution, let's write down what vector a and b are. Vector a is the real part of our eigenvector. So that is going to be equal to 2 minus 1. And then b is the imaginary part. Let's go up here to vector v and let's just add on a plus 0i so that we can see that vector v is going to be equal to 0 minus 3. We can now write down our solution. X of t, pull that down a little bit, is equal to c1 times vector a, which we just found to be 2 minus 1, cosine beta t, beta is 3, so we have cosine 3t. Now we watch out for our sign. This has to be a negative. And then we have vector b, which is 0 minus 3, times sine beta t, so that's sine 3t. And all of this gets multiplied by e to the alpha t, and alpha was minus 2. Now we have our second piece, so we have plus c2. We now have vector a again, so this is 2 minus 1. But now we have a sine beta t, so that's sine 3t. Now we have a plus, and we have our vector b again, 0 minus 3. And we have now a cosine 3t. And all of this gets multiplied by e to the minus 2t. Now we really need to do just one more step and rewrite this just so it's a little bit easier to read. We're going to write this as x of t is equal to c1. Now we're going to combine the vectors in our solution. So the first component is 2 cosine 3t. And then our second component is going to be minus cosine 3t minus a negative 3, so that gives us a plus 3 sine 3t. And this multiplies e to the minus 2t. And now hang with me, we have one last part. We have c2. Now we're looking at our second set of vectors, and we're going to combine those. So we get 2 sine 3t for our first component, and then our second component is minus sine 3t minus 3 cosine 3t. And this is also multiplied by e to the minus 2t. And here's our final solution.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.